So just as a quick review, because we did actually cover this a little bit on Tuesday, a bond can be polar, which is something like being in between being ionic and covalent due to differences in electronegativity values. And so, make this a little bit smaller. Don't need quite all of that. So your table of electronegativity values is right here. I will give this to you on the exam. You do not have to memorize it. Or rather, I'm not going to give it to you because I'm not there. You're there. You're going to print this off. It's on the front page of the course website, and you're going to keep it with you while you're taking your exam through Proctorial, right? So that electronegativity values and equations sheet, that's what this is. And so to know whether a molecule or a bond in particular is polar or nonpolar, you just have to compare the two things that are bound together and subtract the smaller electronegativity value from the larger electronegativity value. And then by telling the difference there, you're going to look on this little chart, and I will not give you this chart on the exam. So this you have to memorize. But if you look on this chart, you see the difference that you're going to say, okay, depending on what that difference is, I'm either sharing well enough that we feel like the electrons are pretty well distributed, or we are not sharing well, so the electrons are not well distributed. One of them is being kind of like an electron hog and hogging those electrons. And of course, when you hog electrons, those electrons have a charge, and so you get a little bit of that charge. So just as a quick reminder, we'll look at section 2 of your worksheet here. So section 2 of your covalent properties worksheet has you doing exactly this. So you look at the HCl or the ClN or the SF bond. We're going to say this atom's bonded to that atom. We're going to compare the differences in electronegativity values to see if something is polar. Now, one thing I do want you to know, although I'm not going to test you on it explicitly, okay? This is a spectrum. Maybe I'll test you on it. This is a spectrum, right? It's not, hey, the world used to be black and white and now it's black, white, and gray, right? You start, if your difference is 0, you are completely covalent. And then if it's 0.1, 0.2, 0.3, you're pretty much just nonpolar covalent. Over here, you are mostly nonpolar, and here you're ever so slightly polar, and you're moving into moderately polar, up to highly polar, to practically ionic, to basically ionic, to completely ionic. Does that make sense? You guys with me there? That it's a spectrum, and I'm not just, I can give you 3 categories instead of just 2, but it really is a spectrum. Okay, so I could compare, for instance, I could say, compare the CN bond to the CH bond and tell me which one is more polar. And regardless of where I am on this chart, you could say whichever one has the largest difference is more polar. Okay, so let's look at just a few of these here. I think we did this one on Tuesday. So HCl, because the H has a electronegativity value of 2.1, and the Cl has an electronegativity value of 3.0. It's not large enough for you guys to see. So based on that, the difference between the electronegativity values of the H and the Cl is 0.9. And again, you don't get a calculator, so you've got to be able to do that. The difference is 0.9. And 0.9 is greater than 0.5 and less than 1.9, so it's definitely in the polar range. And then we can express that by putting a little, you do this in symbol, then it works. The lowercase Greek letter delta, a plus on the hydrogen because it has the lower electronegativity value, and a delta minus on the chlorine because it has the higher electronegativity value. And that shows that we have that it's a polar bond. And we call it polar because it has 2 poles, right? Like you've got the North Pole and the South Pole in the world, or you've got the North Pole and the South Pole in a magnet. Here you have a plus pole and a minus pole on that bond. There's 2 poles. Do you guys see the 2 poles? Why you call it polar? Obviously, I don't call it polar because it's cold, right? Or because there's a bear there, right? No, I just call it polar because there's two poles. And that's important, as we'll see. Okay, so for the ClN bond, because the chlorine has an electronegativity value of 3.0, and the nitrogen has an electronegativity value of 3.0, then the difference is 0, so this is a non-polar, whoa, that's not gonna work if I do it in simple here. This is a non-polar molecule, because the difference is 0, right? And if I do this for S and F, then we can say, let's see, we'll go. Oh, I'm too lazy to look for it. I can just, it's like a little S with the bottom part closed. So, oh, sorry, the sulfur is 2.5 and the fluorine is 4.0. So the difference between the two of those is 1.5. So that is significant enough to definitely be polar. And so I can do this little delta plus on the sulfur and a delta minus on the fluorine. Everybody feel good about that? Trying to figure out how to get that menu to go out. There we go. Fine. Okay, another way to show that, oh, we're crying out loud. I need different colors. Another way to show that is to show this little vector arrow here. Curses. I think I can put this bar on the side instead of the top. That might help me, but I can't otherwise. Okay, so I can put this little vector arrow here showing the positive end, and then it's pulling towards the negative end. The delta plus always goes to the lesser value, yes, and the larger value always gets the delta minus. That's right, so you get the difference. So 4.0 minus 2.5 is 1.5, and then you say, okay, where am I on this little chart? 1.5 is going to be like here, so that would be in the polar covalent range. Just like that. All right, let's do OP. Is the OP bond polar? And if so, which side gets the partial plus, which side gets the partial minus? Good, it is polar because your oxygen is 3.5 and then your phosphorus is 2.1. So the difference is 1.4, which is the polar covalent range. And that makes the phosphorus the one that gets to be partially positive and the oxygen partially negative. Perfect. How do you guys feel about these? Do you want to do a few more? Okay, let's do FCl. Is the FCl bond polar or non-polar? Good. Which side gets the partial positive? Good, because fluorine is 4.0 and chlorine is 3.0. The difference is 1.0. That's definitely between 0.5 and 1.9. And so then the fluorine gets the partial negative, as you noted, and chlorine gets a partial positive. Good. What about the OH? Good. As Sarah noted, it's polar. The oxygen is 3.5 and the hydrogen is 2.1. The difference of 1.4 is definitely in the polar covalent range. And because the hydrogen has the lower value, it gets the partial positive charge. So we get a partial negative here, partial positive here. Just like that. Okay, let's take it to the next step. I think it might help solidify it. So here we're just looking at individual bonds, but really what we want to be able to do is look at the polarity of an entire molecule. And to do it, for an entire molecule, you actually have to do it for all of the individual bonds in an entire molecule. And then you have to compare the relative locations of your partial pluses and partial minuses in your three-dimensional shape. So I think I told you everything stacks here. If you don't have the right VSEPR shape, you're not going to get it right, okay? But here are some that we're going to practice on in a minute after I do this part of the lecture here. Should probably explain how to do this. Okay, so to be polar, you have to have two poles. And sometimes when you have polar bonds, then they add up to give you two poles in the molecule. And sometimes when you have polar bonds, they cancel out, so you don't get two poles in the molecule. And sometimes you don't have polar bonds, in which case, obviously, there's not two poles in the molecule. So let me give you a couple of examples to see what I'm talking about. So first of all, I think you should understand if the molecule doesn't have any polar bonds, then the molecule itself cannot be polar, because the polarity of the molecule or the existence of a separation of charge is based on the separation of charge here in individual bonds. But here I have two molecules. I have CO and I have CO2. These are both molecules that exist in nature. And in each case, the CO bond is a polar bond. And the reason that it's polar is, of course, that carbon has an electronegativity value of 2.5 and oxygen is 3.5. So the difference is 1. It's definitely polar covalent so far as the bond goes either way. And here in this molecule, the molecule is made only out of this bond between the two of them. So you have that separation of charge in the molecule itself. Whereas here, this molecule has two of those bonds, and it is a linear molecule because you only have two electron sets. So I've drawn this in the correct shape. It's linear. And you see you've got a polar bond pulling this way and a polar bond pulling this way. And if you look at this kind of like a tug of war, if you're looking at those arrows, you can see how they kind of cancel out, all right? So Erica says, well, we always have only two atoms. And the answer is absolutely not, right? This was just a great introduction to what we're going to do next, which is to look at molecules which have more than two atoms, right? And figure out what's going on at each of those positions. So for this guy, yes, I have polar bonds, but they kind of cancel out. They're pulling equal and opposite directions. And this guy only has one, so he's not canceling out. The way that I want you guys to look at it, I feel like is the most useful, is to remember that to be polar, I have to have two poles, right? I have to have a plus pole that's in a different place than a minus pole. So I'm going to call this the line test. Can I draw a line, a straight line? That was a terrible straight line. Can I draw a straight line anywhere in the molecule that puts all the negatives on one side and all the positives on the other side? If I can, then I have two poles. This is a polar molecule. But here, there's not any place that I can draw the line, right? If I draw the line down the middle, I have minus poles on both sides. That doesn't work. I can't draw a curved line, right, to separate the minus poles from the plus poles. That's not how it works, right? So because the minuses are on the outside and the pluses in the inside, as opposed to being on the left side and the right side, this is a nonpolar molecule. And I'm not saying nonpolar bonds. I am very specifically meaning here nonpolar molecule. Altogether, the molecule is nonpolar because of the geometric shape and distribution of those individual bonds. Are you guys with me a little bit? Okay, I'll show a few of these here. A couple other examples. So I have here four molecules. I have CH4, NH3, H2O, and HF. And actually, the NH3 has that shape because it's this trigonal pyramidal, right? So I don't necessarily have to show these dots when really what I'm trying to do is show the polarity, but that might help you understand why this one is bent and this one has this pyramidal structure and this one's just linear. So the FH bond is polar. You see the bond polarity shown in black, and the overall molecular polarity mimics that because there's no other atoms there. So the overall molecular polarity is in blue. Here, my OH individual bonds polarities are shown in black. And then overall, because it's pulling electrons this direction and pulling electrons this direction, overall it's pulling electrons that direction. So you can see it in the vector shape, or again, you can do the line test. There's your straight line that puts all your positives on one end and your negatives on the other end. So that's showing overall that is a polar molecule because the molecule has a plus pole and a minus pole. For the NH3, again, I have 3 individual bond polarities and they all cumulatively are pulling upwards, okay? And you end up with the top part of the molecule has a negative pole and the bottom has a positive pole. So there is a separation of the poles there. So this is a polar molecule. And then we see here for CH4, it doesn't have any polar bonds because the difference between the carbon, which is 2.5, and the hydrogen, which is 2.1, the difference is 0.4. So it's just enough that it's not really polar. And so we don't put any deltas, we don't worry about it, we just say it's nonpolar. Oh, I guess I put that there. All right, so here it is a sum of both the individual bond polarities and the shape. You have to put the both of those together to see it properly. So let's look at a couple of the ones from our worksheet and kind of practice that. If we are looking at the SO3 molecule, and I can just tell you to make it easier, the S is 2.5 and the 3 has oxygen has an electronegativity value of 3.5. The difference is 1. So is the SO bond polar? Yes, the SO bond is polar. Okay, so I'm going to put a little delta minus on each O because it has the larger value. A little delta plus on that sulfur. That's representing this bond. And now I will also do it. There's delta plus on that O and a delta plus on that sulfur representing this bond. And now we have a little delta minus on this O and a little delta plus on that sulfur, and that represents this bond, okay? Never at any time do I try to do silly math using 3 oxygens each at 3.5 and multiply or something or anything like that. Instead, I'm just going to look at each bond individually the same way that I did here, okay? And it's easy when they're all the same because then I just know I apply the same, but I look at each one individually. And Erica says, but the overall molecule is not polar because it's pulling in opposite directions equally. And that's correct. That's exactly right, Erica. It's like a 3-way tug-of-war. If you're looking at the polling, or if you're just looking for the line test, right? Does it pass the line test? There's not any place that I can draw a line that separates the positives from the negatives, unless I'm drawing a circle, right? That doesn't count. It has to be a straight line. It has to be a straight line that puts the plus poles on one side and the minus poles on the other side. So this molecule then is in fact nonpolar. Nonpolar. Oh geez, become accustomed to using my text thing here. Text tool. Okay, nonpolar. All right, so the NH3 then, is the NH bond polar? Yes, nitrogen has electronegativity value of 3.0, hydrogen is 2.1, the difference is 0.9, good. So it's definitely polar. And so if we say which of these gets the partial plus and which of these gets the partial minus? H gets the partial plus. Okay, so partial plus on this H, partial plus on this H, partial plus on this H, and then of course this bond gets a partial plus from the hydrogen and a partial minus on the nitrogen, and this bond gets a partial plus on the hydrogen and a partial minus on the nitrogen, and this bond gets a partial plus on the hydrogen and a partial minus on the nitrogen. And is this molecule polar then? Yes. And hopefully you can see it passes that line test. You can just stick the line right there. When I say the line test, it doesn't have to be up or down, left or right. You just have to be able to draw it somewhere, right? So this line was a horizontal line. Over here we were did like a vertical line. Wherever you can put it, if you can separate the minuses from the pluses, then you can see the two poles, hopefully. Okay, what about this molecule, H2SE? Is the HSE bond polar? No, it's not. It's not, because hydrogen has an electronegativity value of 2.1. Selenium has an electronegativity value of, wait, it's not 2.5. What is it? It's 2.4. There we go. Difference of 0.3. We don't consider it polar. We don't put little deltas. We just say, hey, that's not polar. Yeah, non-polar. Okay. All right, what about the CBr4? Are those bonds polar? Okay, Sarah says these bonds are not polar. That's right, because the carbon has an electronegativity value of 2.5. The bromine has an electronegativity value of, okay, what's bromine? Is that 2.1? 2.8. Difference of 0.3. So we don't even draw little deltas. We just say, hey, you know what, that's non-polar. Easy peasy. All right, this one's tricky. HO and a Cl. So hydrogen is 2.1, oxygen is 3.0, and the chlorine is, sorry, oxygen is 3.5, and the chlorine is 3.0. Okay, so again, we're going to look at the molecule itself. We will never compare the hydrogen to the chlorine because the hydrogen is not bound to the chlorine. So chlorine is not going to steal the hydrogen's electrons in a shared bond here because there's not a shared bond there. Does that make sense? Okay, so we're just going to compare, say, H to O. Is the OH bond polar? Yes, because the difference is 1.4. So the hydrogen gets to be partial positive, and this oxygen gets to be partial negative. Okay. Is the OCl bond polar? Good. Sarah, I love it. Sarah says slightly. Perfect. That's a great way to remember that we're here at the spectrum, right? If it's 0.5, I'll call it slightly polar. It's still polar a little bit, measurably, but not a ton. One thing we could do to show that, if we wanted to be specific, we might draw like a much smaller partial positive there and a much smaller partial negative on this end, right? To distinguish it from the larger partial negative, but it doesn't really matter. Yeah. Okay, so then is this molecule polar overall? Sarah says it's polar. Why is it polar? The line test. Oh, good. I'm glad that you guys can see that. So if you use the line test, you could draw a line right here. You get all the positives on this side and all the negatives on this side. Excellent. Does that make sense? Are you feeling confident about these? Do you want to do a few more? Okay. So what I'm going to do, I'm going to pull these from the worksheet. And of course, the worksheet, as it does, it kind of builds you up, right? The first question was to tell me what the electronegativity values were. Second question says, look at individual bonds. Third question says, look at this whole molecule. And the fourth question just tosses you in and says, oh, hey, by the way, here's the formula. Can you tell me if it's polar or nonpolar? And of course, to get there, you have to first determine the Lewis dot structure so you can get the correct shape, so you can apply the individual bond polarities to see if the molecule is polar and nonpolar, right? You might say, rude. But actually, I tried to pick ones. These were on your covalent structures worksheet that we did yesterday. So like if you have your notes, you can go dig back in those and pull them back up so you don't have to write them out all over again. But it's good practice because chances are you'll have to do this a few times on the exam. So I'm just going to toss you in and have you say, let's look at SO2. Help me get there from start to finish. What's the first thing I need to do? Okay, so step one, I need to do the Lewis dot structure, which, as you guys noted, you start by counting the valence electrons. All right, so how many do I have here for valence electrons? Perfect. 6 plus 2 times 6 is equal to 18 electrons. All right, and now what? Sulfur's in the middle. Good. That's exactly right. So I'm going to put oxygen, and then a sulfur, and then another oxygen. Okay, then what? Single bonds. Perfect. Then what? Okay, so electrons on the outside. Sarah, I'm not sure what you want me to fix. There were 6 from the sulfur plus 2 times 6 from each oxygen, right? Okay, all right. Okay, so count the electrons. I've used up 4 here, so now I have 14 left. Good. I'm going to put those on the outside to fill shells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You guys are really good at this. I'm impressed. Now what? Okay, so hang on. If I've used 12 by putting them around the outside, I've got 2 left, and they'll go on the central atom. Did I use? Okay. So now that they're on the center, now that I've finished doing all the electrons, now we can put a double bond. Good. Doesn't matter which oxygen I take it from, doesn't matter which of those electrons I move in, but there it is. There is my Lewis dot structure. Well done, guys. That was step 1 with all of its attendant steps, okay? Now, step 2, what do we need to do? Geometry, so VSEPR shape. Valence shell electron pair repulsion. So that's going to give me the shape. Okay, so what is the shape of this guy? Good, Sarah says it's bent. Hopefully you guys can see. You have 1 bonding interaction there, 1 bonding interaction there, and a lone pair there. That is 3 electron sets. And so that's going to be arranged like a little triangle. And then if you're looking at just the atoms, we call that bent, right? Okay, so what's the next step then? Yeah, use the electronegativity of each atom to determine individual bond polarity, right? So the electronegativity value for sulfur is what? 2.5. Good, good. And then oxygen is what? 3.5. So is the SO bond polar? Yeah, it is. Zachary says yes. Okay, so which side gets the, or what does the sulfur get? Does the sulfur get the positive or the negative? Delta positive for the sulfur, delta negative for the oxygen. That's for this bond. Now for this bond, delta negative for that oxygen, delta positive for the sulfur. Is the molecule polar? Yes, there's your line right there. Perfect. So this is your fourth and final step to apply the bond polarity to determine molecular polarity. You did it. That is all the steps. Alexander, how do you know what? The line test, yeah, that's how you know it's polar. It's the line test. You can group all of your positives on one side and all of your negatives on one side, and that basically tells you that you have a positive pole and a negative pole. You have two poles, and that's what makes it polar. And the side that's positive is the one that has all the partial positives, and the side that's negative is the side that has all the partial negatives. Yeah. Good. Okay, let's do one more. Let's do one more. You guys are great. You're doing great on these. I mean, it all builds, but if we've got a solid foundation on steps 1 and 2, then I think these other two steps are not as challenging. It doesn't matter where your line goes as long as it's the middle, right? So this one, Chase asked if it was, doesn't matter, right? So this one was horizontal. This one was at an angle. I mean, these are objects, right? You can look at them from any angle that you want. And so that line would move depending on what perspective you're using for that molecule. So it doesn't have to be a horizontal or vertical or anything. Just has to be a straight line. It does have to be straight. Okay. Let's do CH2F2 because it's got several different atoms there, okay? So help me with CH2F2. We've got to do step 1, draw the Lewis dot structure. So what do we need to do there? Count electrons. Great. How many do I have? Good. 4 from the carbon, plus 2 from each hydrogen, plus 7 from each, I should say 2 times 7. 7 from each fluorine, 14, 15, 16, 20. Perfect. Okay. Then what is in the middle? C. Okay, so H, C, H. That doesn't matter where I put the F's or where I put the H's, because remember, this isn't showing anything about shape. It's just showing who owns what electrons. Okay. What next? Single bonds. 1, 2, 3, 4 single bonds. How many electrons did that use up? Yeah. 8 single bonds. So how many have I got left? 12. Good. All right, so what do I do now? 6 on each F. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And now what do I do? Yeah, if I evaluate the structure, I've just used up 12 more electrons. I'm a lot of electrons. Everybody's happy I don't need lone pairs, so my Lewis dot structure is great. So I move on to the VSEPR theory, and I've got 4 electron sets because I have 4 single bonds. That gives me a tetrahedral shape. Okay, so if I want to redraw this as a tetrahedron, this is tricky. Again, these are 3-dimensional objects. I can look at them from any perspective I want to, but depending on the perspective that I use, it may be easier or less easy to see that potential polarity that I'm looking for. Okay, so here I put the fluorines on opposite sides, but here I'm going to try to group them together. I'm going to put a fluorine here, put a fluorine here, so both fluorines on one side of the molecule, both hydrogens on the other side of the molecule. Okay, now step 3, bond polarity. What are my electronegativity values for my C, H, and F? Sarah's on top of it. Okay, so because the carbon is 2.5, the hydrogen is 2.1, and the fluorine is 4.0, we've got some interesting things going on here. The carbon and the hydrogen bond have a difference of 0.4, so that is considered to be nonpolar. I don't even write little deltas. I just ignore it. I just say it's not polar. The hydrogen and the fluorine have a difference of 1.9, but they are not attached to each other, so I'm not going to even worry about that. Instead, I'm looking at the actual bonds that are present, and the carbon with fluorine has a difference of 1.5, so that is polar. And what is the F going to be? Is that going to be positive or negative? Negative. Okay, so the F is partial negative for this FC bond, and that carbon is partial positive for that FC bond. Good. And for this CF bond, the F is partial negative, and the C is partial positive. Good. And I just ignore those hydrogens. They're not polar. I don't care. So that is it. There's my individual bond polarity. And then as Sarah noted, you just draw the line here. I group all my negatives on the one side, all my positives on the other side. There are 2 poles, and the overall molecule is polar. That's it. A lot of steps to get there, right? But I feel like you all have a solid foundation on those. Excellent. Okay. Let's look at, oh boy, let's take a 5-minute break. We'll come back at about 8:50, according to my watch. And we'll move on to intermolecular forces.